Hello, everyone. This is a sort of a video walkthrough, I guess you could say, of the first practice district assessment. Your district assessment will be on Tuesday, so that's the day right after Easter break. So I thought I'd just walk through every single problem, and then you can fast forward to whatever part you need to, or watch the whole thing. I don't care. So number one is the general standard form of a quadratic. That is going to be y equals ax squared plus bx plus c. Number two is the general form, but vertex this time for a quadratic, and this one's going to be y equals a times x minus h squared plus k. So those are just kind of, you know, you're going to need to transcribe that onto the test. So make sure you know how to write the general standard form and the general vertex form, and they're just like that. Number three is something you took a quiz on, and what we're going to do here, remember, is we're trying to get it into vertex form. So we want to pull four. Whatever numbers on the x squared we pull out. So our next step is going to say y equals, let me fix that, y equals 4 times x squared plus 6x, and then you leave a blank and you move the 33 off to the side. And then you complete the square. So you take half of the number that I'm underlining. So half of plus 6 is plus 3. And then you square that and you get 9. And so I'm going to add 9 right here to complete the square. So remember, we need to know what that 9 actually is. It's not really a 9. You have to multiply this 4 by that 9. 4 times 9 is actually plus 36. So the opposite of plus 36 is minus 36. So I actually have to subtract 36 to make it go away. And then it's basically done. Now you just have to clean it up. So I'm going to say 4 times x plus 3 squared minus 3. And just always remember that this number over here, the one that I'm underlining in green, is always going to be the same as what you do in the factoring right there. So that should help you. Anyways, that's the final answer for number three is right there. Number four, you're just going to use words. So to describe transformations, you just say the things that are going to happen. I don't actually need you to graph this one. So let's talk about, there are four transformations. So first off, the negative sign is going to cause the graph to invert, or you could say like flip upside down. All right. The next is the 4, and that's going to cause the y values to change 4 times as fast. Okay. So the negative had its own causes a transformation. The 4 causes a transformation. The next transformation that we see is in the parentheses, we have a plus 3. So the plus 3 is going to cause the graph to move to the left 3 units. And then finally at the end, we have a plus 5. That's this guy. And the plus 5 at the back is going to cause the graph to move up 5 units. So the modifiers in this problem, again, are the negative sign, the 4, the plus 3, and the plus 5. And those are just simple descriptions of what each of them does. No need to graph that one. Number 5, we're going to go through and just follow each of the steps. So it does say to sketch the graph when we're done. So the amplitude is going to just be the term that can be used in regards to that number right there. So the amplitude is 1/3, we say. And all that simply means this time is, again, we talk about the y values. The y values, oops, sorry about that, change 1/3 as fast. So you'll remember what that means is when we graph, like if we normally go up 9, we will go up 1/3 of that. We'd only go up 3. Or if we were going to normally go up, say 4, we would divide 4 by 3 a third of 4 is 1 and a third. So again, all your y values. What it does is it essentially makes the graph look fatter. That's the kind of the terminology that we've been using. And I could, by the way, say the same thing if I go back up to question 4. When we talk about this number 4, we could also, in addition to this, you would want to have this in your description, but you could also, if you wanted to, add that it makes the graph look skinnier. I've never written the word skinnier, but I think that's how it would be spelt. So, and then this one is fatter. And that's all happening because of the y's and how fast they change. So the second part B, is the y-intercept. And what you need to know for now and for any other math class that you ever take is that to find a y-intercept, you simply 100% of the time change all of the x's that you see into 0 and then work it out. So if you go up here into the problem and I'm going to erase some stuff now because it's on video, so you can go back if you want to see it. I'm going to go up here into the math problem or the function, and I'm going to change that x right there into the number 0. And then it's going to look like this. It's going to be 1/3 times 0 minus 3 squared minus 7. And then from here, you just do the math. 0 minus 3 is -3. -3 squared is 9. So you do 1/3 of 9 minus 7. 1/3 of 9 is 3. And 3 minus 7 is -4. So the y-intercept has to be at the point 0, -4. Vertex is just given to us in this problem because this function is written in vertex form. And so vertex form just tells us that the x coordinate of the vertex is going to be +3, and then the y coordinate of the vertex is going to be down, so -7 like this. So the vertex is at this point right here. So what I want to do first is just graph a couple of points. And so I'm going to go back to the y-intercept, which I erased, which was 0, -4. And these 2 points right here are going to tell us a lot about this graph. So the 3, -7 is right 3 down 7, so right there. 0, -4 is right here, like that. And at this point, the symmetric point comes into play. And the symmetric point is merely just a reference to a point that is symmetrically across from another point. So if this is the y-intercept kind of here where I'm wiggling my pen, then I would just go straight across from that. And there has to be another point right here, we would agree. Because relative to the vertex, it's up 3 and out 3. So we can now add another point right here. And so just kind of do what we always do and just find some more points. And so, we would go out 1, up 1/3. We'd go out 2, up 1 and 1/3. We already have our out 3, up 3. We'd go out 4. 4 squared would normally be 16, so we're going to go up 16 divided by 3, which is 5 and 1/3. And so on and so forth. And so you just kind of keep going with this. I'll do a couple more. So if I go out 5, it would normally be 25. 25 divided by 3 is 8 and 1/3. So there's 6, 7, 8 and 1/3 is right there. And we can go again. If we go out 6, normally it would be 36. 36 divided by 3 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can fit one more in here. So if you go out 7, 7 squared would normally be 49. And 49 divided by 3 is 16 and 1/3. So I'm going to go up. I know this is 12, 13, 14, 15, 16 and 1/3 is right there. So that would be about the most high quality graph that we could make. And from here, I'm just going to sketch this. I apologize if it looks really, really bad, but this is what your graph should look like. Oh boy. So it's not terrible. I could have done a lot worse than that. So there you go. So that's all the stuff there. So again, remember the amplitude is 1/3, and then if you rewind the video, you can hear the description of that again. The y-intercept is right here. We put x in as 0. The vertex is up here in purple. It's just given by the vertex form. And then the symmetric point is honestly not even really necessary, but on a test like this, you would want to name it because it's problem D is quite literally asking you for it. So the answer to part D is right there. 6, -4 would be the answer to the symmetric point. Okay. So that's that. I think that does it for page one. Page two, we're just going to rock through these just super fast. So it says to simplify each one. For the first one, 300, you would break it into the square root of 100 and the square root of 3, which winds up as a final answer of 10 root 3. For the square root of negative 12, I would just think of it as the square root of 4 and the square root of 3, which is 2 root 3. But you do have to add an I because it's imaginary because of the negative inside. On the third one, I squared, we know is equal to negative 1. So this is really just negative 8 times negative 1. Final answer is positive 8. On this next one, we know that I to the third is equal to negative I. And so if you just multiply 7 by negative I, you just get a final answer of negative 7I. Next one, again, just ignore the number in front. Okay, anytime there's a kind of a hang-on number, just let it go in timeout for a minute. We're going to break 128 up into root 64 and root 2, which is 8 root 2. But then what happens is these two numbers here and here have to multiply together because they're both rational. So we wind up with a final answer of negative 32 root 2. On I to the 57th power, remember you have to take the 57, oops, sorry about that, the 57 and divide it by 4. That's 14 with a remainder of 1. Your calculator would say 0.25. So if the remainder is 1, then we know that that means that we get an I. So the answer to this is just I, because the remainder is 1. This next one, you're going to break down root 45 into root 9, root 5, which is 3I root 5. And then again, the rational numbers are going to multiply. 7 is rational. 3 without the I part is rational. So you're going to wind up with 21I root 5. And then this last one, we all know by now that I to the fourth just quite literally equals 1. And negative 55 times 1 is just negative 55. Question 7 asks us which one of these are imaginary, and the answers are, I'll circle the ones that are imaginary, but you still need to list them. So that's imaginary, the one I just circled, because it's got an I in the final answer. If the I survives and it winds up needing it at the end, then it's an imaginary number. So this is imaginary, and this. So the ones I've circled are imaginary. So I would personally write them down in their original state. So I would say which ones are imaginary? The square root of negative 12. Oops, I can't see that one up there. 7I to the third. I to the 57th. And 7 times the square root of negative 45. So those are imaginary numbers because when simplified, they still require the use of I. Question 8 about the brick is just going to be a vertical motion problem. The first thing we notice is that it says feet. So we're going to use our negative 16 model. So we're going to say the height of the brick is equal to negative 16 t squared plus. The next thing we would put is the initial upward velocity. The thing is, when something is falling or dropping, it has no initial vertical velocity. So I can skip the middle term, which would normally be v velocity times time, but there's no velocity at the beginning. All I need is the initial height. It's dropped from a building that's 86 feet tall. So I'm going to put 86 here. At this point, you could use this model for anything, but this particular problem says that the brick is going to be 25 feet from the ground. We want to know how long it took to get there. So we're going to put 25 in place of h because 25 is a height. So we're going to say 25 equals negative 16 t squared plus 86. And then a quadratic like this should not be quadratic formula. That's overkill. I'm going to subtract 86 from both sides, get negative 16 t squared equals negative 61. And then I'm going to type 61 divided by 16 into my calculator, and I'm going to get 3.8125. So time squared is not what we're after here. 3.8125 is all really cool, but it's not the answer. What I need is to take the square root of both sides of this equation. So if you take the square root of 3.8125, and then you round it to the nearest hundredth, like the problem says, time winds up equaling approximately 1.95 seconds. All right, so that's that for problem number 8. nothing to it. Question 9 takes some doing. I don't know if I'm going to have enough time with what I'm doing right now to finish this, so I may wind up making a second video and posting it. So we'll see. So for number 9, we have to turn all of these into points. So what we know so far is that at 1 second, what is it? A baseball has a height of 83 feet. After 2 seconds, the baseball has a height of 91 feet. And after 3 seconds, the baseball has a height of 67 feet. Each of these is going to be plugged into this red equation. Y equals a x squared plus bx plus c. So for the first one, we're going to write y equals ax squared. Since x is going to be 1, it's just going to be a. And again, since x is 1, it's just going to be b plus c. And we're just going to keep doing this for each point. So like the next one's going to be 91 equals x squared is 4. So we put 4a plus x times b, which is 2 times b plus c. C has no x multipliers. And then the last one is 67 equals 9a, because that's x squared, plus 3b plus c. This is a triple system, so in the interest of saving some time here, I'm not going to go through the act of solving this. What I can tell you, I mean, I could get you started on the process if that helps, but what you want to do here is definitely use elimination. And so personally, I would multiply the top equation by -1. And then that's going to change the top row into -83 equals -a minus b minus c. And then what you want to do is take that old equation and swap it out with this new equation. And then you should be able to see from here that using elimination is pretty simple. We're just going to do row 1 plus row 2. And then we're going to do row 1 plus row 3. Anyways, when all is said and done, if you want to go over this, just come see me. But when you're done, you should wind up with an A value when you solve your triple system of -16, a B value of 56, and a C value of 43. And what that means is that our final answer to question number 9, part A, is right here. It is y equals -16x squared plus 56x plus 43. So that's it for part A. Part B says to make a sketch of a graph. And so what we want to do here is just sort of, do the best we can. I'll walk you through kind of what I did. First thing you need is the vertex. Like you're not making a graph without a vertex. And so to find the vertex, we are going to do -b over 2a. So the vertex can be found at -b over 2a, and that comes out to be 1.75. And then if you put 1.75 back up into those x's that I just circled in my model, you will get 92. So that means that we have a point, our vertex is up at 1.7592. So I'm going to make a scale here. I'm going to just go all the way up to 100, and I'll mark the halfway point as 50, and then I'm just going to notch these off and go by tens. So 60, 70, 80, 90. And then these ones don't matter as much, but I'm going to do them anyways. And so I've got 10, 20, 30, 40. And then we want to label that as height. And that is measured in terms of, in this case, feet. For this, I'm just going to make some marks because there's not a lot of time that elapses in a problem like this. And so I'm just going to do 1, 2, 3, 4, 5. And I'm going to label that as time in seconds. All right, so for this one, we're just going to put in some points. And so the first one is the vertex. And so for that, I'm going to go to about 1.75, which is right about here. And I'm going to go straight up from that to about 92, which I think is probably right about here. And I'm going to make my vertex. The next point we really need is the y-intercept. The y-intercept is going to carry a lot of weight here. And as you know from earlier in this explanation, the y-intercept can always be found by putting zeros in place of the x's. So the y-intercept is obviously at 0, 43. So I'm going to make a new point now for the y-intercept. That's right here. Well, that's probably about close. And then the key here is you want your symmetric point to be across from that. And then at this point, we'll have a good enough sketch. So if you kind of see where these two, oops, kind of missed there. My bad. Let me see if I can fix that a little bit. So you want to figure out that the symmetric point is going to be the same distance away from this symmetric or this axis line. So since it's 1.75 over, it's going to be 1.75 to the right. And that's going to get us right here to 3.5, which is right about here. And then you can erase these sketch lines if you want to. You don't have to, but I'm going to. And then to make the graph, you would just connect the dots at this point. It does not have to be beautiful. It is just a sketch. But I kind of will stop the graph there just because I don't really see the point in going into the negatives at this point. So there's a decent sketch. And then question letter C says, on the way down, the ball flies into a hole. So all I need to do is put 5 in place of my x's. So I'm going to do y equals -16 times 5 squared plus, I think it was a 56. So plus 56 times 5 plus 43. And if you work out that math, plug it into your calculator, that's fine, but it'll wind up being -77. So to answer this question, we can just use a sentence and say the hole is 77 feet deep. And that is that. So I'll probably make another video like this for the second practice DA, but that's it for now. So let me know if you have any questions.